Hello students, this is the second video on moment of inertia. So in the last video we discussed about the moment of inertia of certain specific objects, and in the last section we discussed about the parallel axis theorem. Now we can give a proof to the parallel axis theorem. The parallel axis theorem, it states that the moment of inertia of any rigid body about an axis is equal to the sum of the moment of inertia of the body about a parallel axis passing through the center of mass of the rigid body plus the product of the mass and square of the perpendicular distance between the two parallel axes. Now if I0 is the moment of inertia of the rigid body about an axis passing through the center of mass, now if z dash is some axis parallel to this particular axis and the moment of inertia about this axis is I, then I and I0 are related by the equation I equal to I0 plus m into d squared. M is the total mass of the rigid body and d is the perpendicular distance between these two. Now let us give a simple proof for this theorem. Now I am not following Kleppner in this particular case, so I have referred the text J.C. Upadhyaya. Now let m be the mass of a rigid body. So this is the rigid body is shown in the figure, and its total mass is capital M. Capital M is the mass of this rigid body. And now AB is an axis passing through the center of mass of that particular rigid body, and DE is another axis. It is not passing through the center of mass, but it is passing through but it is parallel to this axis AB. Now D is any axis, and then we have to imagine an axis passing parallel to it but passing through the center of mass. Okay. See, AB is on axis passing through the center of mass but parallel to the axis D. Now small d is the separation between these two axes. Now let I be the moment of inertia of the rigid body about the axis DE, and I0 is the moment of inertia about the axis AB. Then we know the parallel axis theorem states that I is equal to I0 plus m into d squared. M is the total mass of this body, d is the perpendicular distance between these. Now that is I is equal to I0 plus m d squared. Now you consider a particle of mass m at the point P. At point P at a distance x plus d from this axis D. So it is the point P we have considered is at a distance x from the center of mass, and its distance from this axis is DE is x plus d. The perpendicular distance is x plus d. Now the moment of inertia of the particle about the axis DE is the mass of this particle plus square of the perpendicular distance, that is m into x plus d all squared. Now we can write this moment of inertia of this small particle as di. Now this body can be imagined as made up of a large number of such small particles. So total moment of inertia of the whole body is equal to I is equal to sigma into di. So that is I is equal to sigma di is equal to sigma m into this m into x plus d all squared. That is equal to, on expanding this x plus d all squared, we will get x squared plus d squared plus 2xd. So that is, first term will be m into x squared, sigma m into x squared plus sigma m into d squared plus then 2mxd. So we can take this 2d outside, 2d into sigma mx. Now we know the definition of the center of mass. The center of mass is defined like this. M is the total mass of the body, R is the position vector of the center of mass, m r is equal to, if we have a system of particles sigma mi ri. Now, so this capital R is the position vector of the center of mass. Now, if we are taking center of mass as reference, center of mass as the origin, then R will be equal to 0. So, sigma mi ri will be equal to 0 if we are taking center of mass as the reference point. Now, you can see sigma mx means x is the distance from the center of mass. So, with respect to the center of mass, we are taking m into x. So, m into x is the, we can call as the moment of the mass about the center of mass. Now, some of these moments about the center of mass will be equal to 0. So, sigma mx will be equal to 0. So, this term reduces to 0. So, the moment of inertia will be equal to, I is equal to sigma mx squared will be there and sigma md squared will be there. Sigma mx squared plus sigma md squared. What is sigma m into x squared? M is the mass of this particle, x is the perpendicular distance from this axis AB, center of mass. Sigma mx squared gives what? The moment of inertia of the body about an axis passing through the center of mass. Okay. So, sigma mx squared simply gives I0. Then, D is the separation between the two parallel axes. So, in this case, sigma m into d squared is a constant. So, d squared can be taken outside. D squared into sigma m. Sigma m will give the total mass of this body. So, we will get I is equal to I0 plus m into d squared. So, this is the proof of parallel axis theorem. Now, so in the previous video, we discussed about the example. One example, that is the moment of inertia of a rod about an axis passing through the center and perpendicular to the length. So, actually this rod is passing through the center of mass. And we got the moment of inertia as ml squared by 12. So, this is the moment of inertia we got. Now, again we have calculated the moment of inertia of the same rod about an axis passing through one end of the rod. So, about this axis, the moment of inertia of this rod is obtained as 1 by 3 into ml squared. About the axis passing through the center, we got it as 1 by 12 into ml squared. And about an axis passing through the side, one end, we got 1 by 3 into ml squared. Now, if you know this is an axis, the axis passing through the center means the axis passing through the center of mass. So, if you know the moment of inertia about the center of mass, axis passing through the center of mass, we can calculate the moment of inertia of the body about another axis parallel to this axis. So, that is passing through the side but perpendicular to its length. Now, in this case, this is an axis passing through the one end and perpendicular to its length. So, this is an axis passing through the center and perpendicular to this length. So, both the axes are parallel. So, we know I0 is the moment of inertia about an axis passing through the center of mass. The separation between these two axes is L by 2. So, let us apply parallel axis theorem. So, the moment of inertia about this axis can be written as I. So, I is equal to I0, this moment of inertia about an axis, parallel axis passing through the center of mass, plus m into total mass of the rod is m into this distance d. Instead of d, here we get L by 2. So, d squared, in the place of d squared, we will get L by 2 all squared, m into L by 2 all squared. So, that is I is equal to I0, we know that 1 by 12 into ml squared, that is ml squared by 12 plus ml squared by 4. So, on LCM is 12, so we get ml squared plus. So, here when the denominator changes to 12, we have to multiply the numerator by 3, ml squared plus 3 ml squared. So, you will get numerator, we will get 4 ml squared by 12. So, that is 1 by 3 ml squared. So, we get the same answer. Here also, the moment of inertia of the rod about an axis passing through one end but perpendicular to its length is 1 by 3 ml squared, and we obtain the same result using this parallel axis theorem. Okay. Thank you.